Hi everyone, welcome to Introduction to Lab for week of October 19. We're going to do two exercises this week, exercise 6 and 10 in your lab book, Contemporary Activities by Hoff and Wilkerson. For those of you who aren't in the class and happen to be watching this, the exercise 6 is about angular resolution, and we'll talk in the next week. We'll talk about the telescope and the importance of the telescope for improving angular resolution. A lot of people think the telescope's important attribute is magnification, and really the more important attributes are light gathering capability and angular resolution. And so we're going to work on that in lab this week. And the idea of angular resolution is this. It says if we have this idea that theta is equal to 57.3 S over R if we're measuring in degrees. And we've used this a few times. We're going to use it a few more times, so you want to get used to it. Where this is R and this is S, and that's theta. Now, if something gets far enough away from you, think about the headlights of a car. If the headlights of a car get far enough away from you, at some point you can't tell they're two distinct headlights, and they merge into a single headlight. And that's you've reached the resolution limit of your eyes. That's the smallest angle you're able to see. So theta resolution is equal to the smallest angle you can discern. Now, if you are looking at an object that's dark, that's not glowing, and the one side of the object gets below the other side of the object, one side of the object, the distance from one side of the object to the other side of the object, that's S. So this S could be two different objects, like we just talked about with car headlights, or it could be two sides of the same object. A lot of times you'll read a story in the newspaper where they said, wow, this telescope could see a dime at Mars or something like that. And so it could be the opposite sides of that dime. And if those two things, if theta resolution gets such that you can't see the two different sides as distinct, then the object goes away on you. You don't see the object. It gets too small to see. So there are objects, that are too small to see. Dust mites, for example, are probably too small for you to see. Cells, amoeba, whatever it is that you're looking at that's very small, you can't see, and that's because that object is the two sides merged together. Now, if it's a brightly glowing object, you can see the glowing point of light from it. So stars, by and large, are not resolvable, and so even with a telescope. And so what that means is the theta that comes from one side of the star to the other side of the star divided by the distance to the star, because the distance is so vast. We can't resolve stellar surfaces. So we want to measure this resolution limit, and we want to try it different ways. And so in both of the labs this week, we want to measure this at several different distances. So you're going to start with just your eye, okay? If you normally wear glasses, keep your glasses on. And you're going to try several different R values. And I don't care what R values you choose exactly, but I choose 5 R values and have the distances. Maybe you can play with the resolution chart that you have and see if what distances make the most sense for you. But it might be that you do something like 2 meters, 5 meters, 8 meters, 10 meters, and 15 meters. Or maybe you do 5, 10, 15, 20, 25. I don't know. It doesn't really matter what R is. You're going to find out what S you can no longer resolve, where two objects merge together. So there's a resolution chart in your book. So the resolution chart looks like this. And you can have one of your lab partners move away. You move away from the lab partner, and you see where these start to merge together into where can you still see the dark space between the bright lines? Yes, 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 no. Okay, and so between the last yes and the first no, you can take your ruler and you can measure what that separation is, and that can be the S value. And then the R value is the distance you are away, and theta is going to be the resolution limit of your eye. If that chart's hard for you to see, we do have these other charts that you can use. So you can use these charts, and maybe that's a little bit easier to see where these things merge together. As I back up, you'll see these things start to blend in, and you see them as solid blocks. We also have a few of this kind of chart where you can, if you're so inclined, use this chart, and it's got the separation of the lines in millimeters. You can see that it's not perfect in Xerox. See, the bottom there says those lines are 0.5 millimeter apart, and there's no space between them at all. So this hasn't been Xerox perfectly, so you have to be a little bit careful about that, and maybe it's better up here that you use. But you can slide this down. You can start to slide this up until you see distinct lines. You can see the white space between the black lines, and you can read what those are. Given that the problem with making Xerox sheets like this, or like this, or whatever you're using in your resolution chart, given that problem, you're probably not measuring exactly the resolution. Your resolution is probably, in fact, a little bit better than what you're going to end up measuring here. But you're going to be consistent anyway, from person to person and in the group. And so what I'd like for you to do is make those resolution measurements, and then you have to make judgments. You have to be like Tico and make judgments about your data. You look at the data and you say, oh, goodness, theta resolution doesn't look like it's just jumping around, and it's more or less consistent, and then I can average all of these values. I can say theta resolution is the average of the resolution I got at all these distances. Or are these distances close out here and then getting worse in close? Or are they close in here? And then, so if you took theta resolution and made a graph as a function of r, you might see it looking something like this. Sometimes when we see a graph like that, we never know for sure what's going on. You got to make decisions, right? That's what you as an astronomer have to do, is make decisions about your data. And sometimes you're right and sometimes you're wrong. You don't want to have a lack of confidence in your data, but you don't want to be overconfident about your data. You got to struggle with that. But you might look at that and say, this looks like maybe my resolution is right there of my eye, and this is, I want to use something out there. You make your judgment about the quality of your data. Talk with you. So each person in the lab measures his or her resolution of the eye. So we want every person measuring eye resolution, and when you're done, we want to write that eye resolution on the board in each room so that we can see what the whole class is, and we can take an average of the whole class. So I want you to report to me what your resolution is and how you got there. Did you just average all of these? Or did you decide that one region was better than another? You might go back. You might decide, this data's no good, and I need data out here, so I'm going to go back and take data at more R values than I did initially. Or something along those lines. Maybe out here's no good, and you need to take more points in here. And maybe you just decide 5's not enough to tell what's going on here. I got to do 8. And if you want to do 8, I think 8's great. You make that decision. You're the scientist here, and you're deciding how you're going to go about doing this experiment. But you can, so you're going to report to me what your resolution is, how you got there, and you're going to report to me what your what the class average is, and you'd say that that's a typical for a human being, okay? And so you can do this in degrees, or you can do this in radians. I'd say let's do this in radians. So let's get rid of that 57.3 for this experiment, and let's report theta in radians is equal to S over R, and let's just do it that way so we're consistent from one to the other. So this is one of the big differences between humans and birds. There are a lot of big differences between humans and birds, but a lot of birds have this theta resolution as much as 10 times better than what a human has. So when you think about somebody if somebody calls you an eagle eye, that's what we're talking about. It's the fact that the resolution of a bird of prey in particular, but true of ducks, it's true of a lot of birds. A bird of prey has a resolution limit that's up to 10 times bigger than this. Now, if you go to the optometrist and get your eyes examined, you'll get something that's called the visual acuity. And I don't know what that is exactly. I was going to look that up before I started talking to you here, and I realized I didn't. But the visual acuity is something like just 1 over the resolution. It's something like the inverse of the resolution right there. So the better the visual acuity, there may be constants or something else going on in there, but the better the visual acuity is, the higher number is better. For angular resolution, a lower number is better. You have better eyesight if your angular resolution is smaller. It means you can see a smaller angle at any given distance. You can see a smaller separation of two objects. So you do all of this, and then I want you to build a simple telescope and repeat to see if you can get a better resolution. And the telescope is really remarkably simple that you're going to build. And you're just going to repeat the experiment again. You probably have to have bigger R distances, okay? You probably have to move further away with the telescope because the angular resolution should be a little bit better. The angular resolution is not going to be a lot better, and there's two reasons the angular resolution is not going to be a lot better. One is, man, do we have poor quality lenses that we're giving you to work with. And two is you're going to find out how hard it is to actually look at something through this telescope. So you're going to take a meter stick like this, and you're going to plug two lens holders on there, and then you're going to put two lenses in there, and you're going to look through it, and you're going to slide it until you get a crisp image. And when you get a crisp image, you're going to see probably upside down. So you'll take two lenses. You have choices. Lenses 2 or 1, and lenses 3 and 4. So pick one of 2, 1 and 2, and one of 3 and 4. So you've got lenses 3 and 4. Pick one of 3 and 4, and one of 1 and 2, and put the 1 or 2 in here, and the 3 or 4 in here, and you look through the smaller number lens, through the other lens, and you should see a magnified image, and you should see it upside down. So you should see an inverted magnified image. And it's really tricky to do. A telescope that you would go out and buy, or a telescope that you would use, typically would have a tube. And that tube keeps stray light from coming in. So you're going to have a lot of light that's coming in that doesn't go through both lenses. It just goes through one lens. And that's going to be fuzzy and hard to work with. You're going to look for the sharp, you're going to slide this thing back and forth and look for the crisp image that's in a small circle in the middle that's inverted and magnified. If it's not magnified, if it's smaller, you're looking through the wrong end and you need to swap it around. So you can play with that. The separation between these two lenses is probably going to be, as you get this focus, you want to look at something relatively far away. It's going to be approximately equal to the sum of the two focal lengths, and the focal lengths are written on the bags up here. So lens 3 has a focal length of 20 centimeters. Lens 1 has a focal length of 5 centimeters. Lens 2 has a focal length, lens 4 has a focal length of 30 centimeters. Lens 2 is going to be 10 centimeters. I don't see it written on there. There it is. Yep, 10 centimeters on lens 2. So if you have a lens 2 and a lens 4, 10 centimeters focal length, 30 centimeters focal length, about 40 centimeters between there. Now, if the object's closer, you're going to have to change that if it's not very far away from you. But you can slide this thing back and forth. If you need to bend this out a little bit or bend it in to get a tighter fit or a looser fit to get it to slide better, you can do that. Same up here. If your lens doesn't fit in there very well, you can play with that too. The lenses look like this. And they just plunk. There's your lens, and there's your holder. They just plunk into the holder. Try not to handle them too much like I just did. We'll have some lens cleaning tissues down there for you to work with. And so that one's a little bit too loose. I'm going to bend it together. You saw it was too loose out this way, so I just bent it together. And now I'm going to snap this lens in there, and it should hold the lens. And it does. Yeah, it holds the lens nicely there. I don't know if you can see my eye or not. Yeah. Anyway, that's the thing you're going to do, and you're going to put these two together and do this work, and it should be fun. So I want you to get to exactly the same thing. Your resolution with the telescope, write it on the board, get the average of the classes, your resolution, the average of the class, and then I want to do a ratio. Theta resolution of the eye divided by theta resolution of the telescope, and that's a factor. That's how many times better resolution you're getting with the telescope. And I want you to report that to me. So I want you to show me all your calculations. I want you to show me data tables that have your S's and your R's and your theta resolution. And then I want you to write me a paragraph that talks about how you decided to calculate your theta resolutions and the decisions that you made that went into it. And then I want you to report numbers like this in there and talk about what you've seen. Is the telescope better or not better? One of the issues is the telescope is going to be jumping around all over the place, the image on you. It's going to be hard to hold steady. And so it helps if you can brace your arms on something like this. So you can brace your arms, or sometimes if you have a long stick out there and you can put it on this end of the stick can rest on something, a person's shoulder or a bench, a tabletop or something like that. You're going to have to do some of this work in the hallway maybe. So you'll do this work in the lab, but you're going to we need to stay spread out, but you can spread out in the hallways around Valders and do this, or you can go outside and do it if it's a nice day. You're going to have to go outside to do the other part of the lab. So you can do this either way you want to do this, any way you want to do this. Inside, outside, in the long hallways, but you're going to need, if you're going to go 20 meters or something like 15, 20 meters, that could be quite a distance. At 10 meters even is hard to achieve in the lab, and so you might need to get outside to do this. So for all of this work, report to me how many times better the resolution is with the telescope. And again, it's hard to see the spacing between the lines because you're shaking around. So one of the tricks with the telescope is you need to rest this and hold this firmly, so you don't get that kind of shaking around. There's a lesson in there too. If you're going to go out and buy a telescope to do fun astronomical observing at home, one of the more important things that people often don't realize about a telescope is how good the tripod, how good the mount is, how stable that telescope is firmly held in place, because if it's shaking around, you're not going to see much of anything. You got to have that thing really locked down. You're going to see how hard that is with this simple little telescope that you have here. So that's what I got for you for exercise 6. We'll talk about exercise 10 in part 2. So take care, everybody.